Okay, it's a great pleasure to have Umang Bhaskar visiting us today. Umang did his master's at IIT Bombay, then did his PhD in computer science from Dartmouth. Subsequently, he was a postdoc at Caltech and Waterloo. Umang has done some spectacular work since his dissertation on congestion games, in particular equilibrium computation in congestion games. How do you set tolls to induce certain outcome in congestion in routing games? And more recently, he has been working a lot on voting, and today's talk will be along those lines. So please join me in welcoming.
Thanks for that. Okay, so this is work. So it's on the welfare of truthful voting mechanisms. Basically, we're going to see that for voting mechanisms, if we add the constraint of truthfulness, how is the welfare going to suffer? What do you say about that? What is the cost for truthfulness in these mechanisms? This work started with this work was done with Varsha Dani at University of New Mexico and with Abhik. Abhik is now at UT. He's a master's student. He was a summer intern at TIFR while he was an undergrad. So he started this work and then kind of continued from there. Okay, so let me just jump straight into the problem that we're trying to solve. So there are 4 voters, and they have to choose from among 3 possible construction projects. They can choose to build either a garden, a library, or a playground. Right? These are the 3 candidates they have to choose from. I'm going to assume throughout this talk, my underlying assumption over here, critical assumption, is going to be that each voter has a numeric utility, a cardinal utility for each of the candidates. Right? So the first voter, for example, gets utility 0.4 if the garden is constructed, 0.6 if the library is constructed, and 0, she doesn't like playgrounds for some reason. Similarly, for the other voters, they get some numeric utility such as this. And you would have noticed that there is some peculiarity, some particular thing about the numbers. Is that for each voter, I'm going to assume that the utilities sum to 1. Right? So the sum up for single voter utilities over candidates, that sum is 1. And of course, I'm also going to assume non-negative, so all of this lies between 0 and 1. This is called a unit sum assumption. One way of interpreting this is that the weight of all voters is the same. So if I look at the social welfare, they're all scaled in that sense. No voter is going to be much more important than anybody else. So this is the unit sum assumption. I'm going to stick with this assumption through the talk. We'll use this at various points. At the end, I'm going to ask, well, what happens if we relax this assumption? So, okay, so given this, I know my voters have these unit sum cardinal utilities. My objective is going to be what you imagine. I want to select the candidate which has maximum total utility, right? Candidate which maximizes the social welfare. If this is my objective and this I'm given all of these numbers as input, it's very simple. I'm just going to sum for each candidate the utilities, pick the one which has maximum total utility, I'm good. Right? This is fine. Right, so clearly this is not realistic. This is not realistic in various ways, so we'll talk about that. But hopefully we understand what it is that I want to achieve. Right? There are the underlying utilities. Under some constraints, I want to pick out the one which has maximum total utility. Right, so just some notation. I'm going to use n always to denote the number of voters and m to denote the number of candidates. This n is going to disappear, so forget about that. Mostly it's just going to be in terms of n. And my bounds and stuff are going to be in terms of m. So remember that. I'll point out what the thing is. I'm going to use u to denote utilities. I is always going to be voters. J is always going to be candidates. So the first one is going to be voters. Second subscript is going to be candidates. Right. And this is what I want to maximize, the sum over all voters of the utility of that particular candidate. As we said, this is easy. If you could figure out all of these numeric utilities, I do this something, I'm fine. But there are numerous reasons for which this is not done. Among others, the voters may not be truthful, and this is clearly something that is observed. So, for example, your top candidate is going to lose the election. There's no way that your top candidate can win. So why not put your second rank candidate on top? Right? So this kind of manipulations are done frequently. People have studied how to remove these kind of manipulations. Right. So one reason is that voters may not be truthful. Secondly, they may not know what, or they may not be able to express their exact utilities. So I'm assuming that there exist exact utilities, right? But I'm not going to assume that voters will be able to but voters may not be able to communicate these exactly. And thirdly, even if I know them, like it takes a certain amount of time to fill out a ballot paper 0.44 for the first one, 0.62 for the second one, and so on. Right? So voters may not like these kind of complex voting mechanisms, they prefer something similar. So, right, so there are many reasons why we can't just ask for exact utilities and be done with it. Having said that, I'm going to look at two types of mechanisms. The first type of mechanism does exactly what I said I should not do, which is to look at cardinal utilities. So these kind of mechanisms are just going to ask everybody, give me your cardinal utility, give me all of these numbers that you have, and I'm going to do something with it. And secondly, I'm going to look at ordinal mechanisms, wherein instead of numbers, people give me just an ordering of all the candidates, right? What is your first rank, what is your second rank, third rank, and so on. Despite these disadvantages, why am I interested in cardinal mechanisms? So one reason is that if I prove lower bounds for cardinal mechanisms, these hold for all other kinds of mechanisms as well, right? In some sense, cardinal mechanisms give me the most amount of information, right? So even if with that amount of information I can't do something, I wouldn't be able to do it with less information either. So this is kind of establishes fundamental lower bounds on what can be done in mechanisms. And then secondly, I'm going to be interested in that I throw away the numeric information, I just have these rankings. Now what can I do? Okay, right. So those are ordinal mechanisms. These are my inputs, and I'm going to look at randomized mechanisms. For deterministic mechanisms, again, there's a whole bunch of strong lower bounds. I'm going to be looking at randomized mechanisms for both of these. And this is the notion of when I say ordinal mechanism, well, I have utilities. So I'm going to assume that that a preference order is consistent if what you naturally think is true actually holds, right? So if voter I puts A before B, then it should have more utility for A than for B. And I'm going to make this assumption that that no two utilities are the same for two candidates for a voter. By the way, questions? If there are any questions, please stop me.
It's a one shot, like you're only looking at cases where they submit a ballot.
One of the results will be looking at what happens in dynamics for equilibria. But when I'm not looking at, I am going to be looking at truthful mechanisms. So the one short thing is. Right. So the good question. So how do I define social welfare and ordinal mechanisms? I assume that the ordinal mechanisms come from underlying cardinal utilities, and the welfare will be measured with respect to these underlying cardinal utilities. Right. But I'll actually give a little more detail on that in just a minute. Okay. So given cardinal utilities, this is my expected social welfare, which is what I hope to maximize somehow. So P is the distribution returned by a mechanism. This is the expected social welfare. Like I wondered whether I should keep this picture up. It's kind of trivial, but anyway, let's just pretend that we're on grade 5 and run through this. So these are the utilities of the first voter. The numbers are the actual utilities. So cardinal mechanism get to see 0.4, 0.6, and 0. But ordinal mechanism would only get to see these numbers. And based on these numbers, we'll try to do the best it can with respect to underlying utilities. Right? And just to kind of address a little more in what you were saying, well, what underlying utilities, right? The mechanism only gets to see ordinal. So the answer is the worst case underlying utilities. In the worst case, what would the utilities be? How can I do it with respect to that? The worst case utilities which are consistent with the orders. Okay. Right. So like I said, so we're talking about what are the constraints we're imposing. One of the constraints we said was that I only have ordinal information. Okay. The other constraint I'm going to impose is that whether ordinal or cardinal, I want my mechanism to be truthful. Right. Which means that truth telling is a dominant strategy, so no matter what the other voters are reporting, it must be true that for each candidate, the candidate should be incentivized to tell the truth. Right? It cannot get a better utility for itself by misreporting its utilities, whether ordinal or not. Right? Right. So this is the definition for a cardinal mechanism. For a voter I, given its true utility and whatever else the other voters are doing, given any deviation, my utility is maximized. Blah blah blah. You've seen this before. You know what this is.
Should the left hand side be U prime? Like the P changes, right?
Shouldn't the left hand so this is what is returned by the mechanism, which depends upon what the person reports. And this is what it is for ordinal mechanisms. Ignore the notation. You know what this should be, what this should say. Questions about anything so far? We understand the mechanisms, the input, truthfulness, and so on. Yeah. Okay, so right, so to get a little bit deeper into what we're measuring. So as you know, as we do what we're interested in, not the social welfare as a number by itself is not very meaningful. We would like to compare it to something, and what we compare it to is the optimal social welfare. Right? So I'm going to be looking at the ratio of what the mechanism gets versus if I had a full information setting, if I knew everything, no constraints, what is the social welfare that I would get? And this is what this is defined as. So for mechanism mu returns a distribution P. So this is going to be the supremum. So if this is so if this is ordinal, then this is going to be supremum over all U, which is consistent with the input that the mechanism is seeing, of the ratio of the optimal thing in U, the max utility candidate, divided by the expected welfare that the mechanism is getting. So mechanism mu gives a distribution P. This is the denominator is the expected welfare the mechanism is getting. It's not hard to see that this is always at least 1. Opt is larger than what the mechanism gets. I would like this to be as close to 1 as possible. Right. Does this address your question completely now? So the ordinal mechanism sees this ordering. In the worst case, for all U's that are consistent, I want to minimize this ratio.
So that's a non-elementary question even without.
That's a non-elementary question even with just ordinal mechanisms. Yeah, exactly. Right. Okay, good. So let's just run through examples of some mechanisms. What are some interesting mechanisms to look at? And these will make an appearance later on as well. Here's a trivial mechanism. I just ignore all of your inputs and I pick a candidate uniformly at random. Right? And it's not hard to see, and if you just think about this for 2 minutes, then the distortion for this thing is exactly n. And the reason it's m because I get n over m. What is the total utility? Each voter gets utility 1 over the sum of candidates. So if sum over all voters, I get n. So in expectation, if I pick one uniformly at random, I get n over m. And then there could be a candidate which everybody really likes, has utility 1 for. So the optimal could actually be n. So this gives me a distortion of n. Okay, so let's do something a little bit more sensible. Rather than just throwing away all of the input, I'm going to pick one voter at random. I'm going to ask that voter, okay, you tell me, which candidate do you prefer the most? It's not even looking at all the ordinal information. Just ask the candidate, which candidate do you like the most? And then I pick that candidate. Here also, it's not hard to see that the distortion is at least n. It takes a little bit more thought to think why, but basically here for the worst case, the second rank candidate everybody agrees on. Second rank candidate everybody has utility 1/2 for. So that candidate has n by 2. But there's no way you're picking that one. The first rank candidate is, let's say, just uniform over all the candidates. So if you pick the top one, you will get n over m. You should have got n over 2 if you chose the second one. So this has distortion at least n. This is also not great. But the thing about both of these is that they are ordinal. Like the first one is completely throws out the issue, and they are truthful. Here's something which is a natural mechanism, right? Which makes use of all of the information now. It kind of, for each candidate, it sums up overall, it sums up overall what is the utility of each candidate, and returns to me the max utility candidate. Okay? So let's call this a max mechanism. This is great, this is fantastic, this is cardinal, it's not. And again, it's kind of instructive to our examples where this is not the case, but yeah, this is not truthful. And here's a something which we'll be using. So okay, so now this is a randomized mechanism. Randomized mechanism fixes some. I mean, any mechanism has to choose a point within the m-1 simplex. Right? I fix a subset of this simplex. I fix some ball within this simplex. Right? And now what I do is I pick a voter I uniformly at random. And now for this voter, I'm going to pick the distribution from this range, from this smaller range, which in expectation maximizes this voter's utility. You should convince yourself that this is truthful, right? Because I'm already choosing from within the range that I can choose. I'm choosing what I can to maximize the voter's utility. Okay, so this is truthful. The question is how well does it do in terms of my other factors? Okay, so this is a maybe a non-trivial cardinal mechanism because it actually uses the entire UIs. Maybe hopefully it does something non-trivial. Questions about anything so far? Okay, cool. Right. So let's jump into what we know about these things, right? About ordinal mechanisms, cardinal mechanisms. Right. So ordinal mechanisms. So what's known is the following. And this is kind of the paper which started our work as well. So it's known that if you forget about truthfulness, right? Just the fact that you've thrown away this numeric utilities and you're just looking at the chart and the ordinary means that you already incur a loss of square root. If you pick the worst case utilities, no matter what you do, you will get a loss of square root n in the switching. Okay? So this paper by Rudiger et al. It shows that you can get very close to that upper bound, very close to that square root m log star m. It's iterated log. And they also give a much simpler mechanism, which is something we use as well, which gets order of square root m log. Right? So basically, the message is that the loss of the cardinal utility itself imposes the loss of square root m. Truthfulness on top of that doesn't impose much more of a cost. Just another square root log n factor. Not so bad.
So the second one is truthful.
The second one, we do a little bit of massaging to make it truthful.
Okay. This none of it is.
No. All of this is So unless I say truthful, that's one. Yeah. Okay. So this is for ordinal mechanisms. This is for distortion. This for distortion in ordinal mechanisms. There's also a lot of work in social choice theory on characterizing ordinal or truthful ordinal mechanisms. So what I said previously was not truthful. There's a lot of work on understanding when is a mechanism truthful, when is an ordinal mechanism truthful. And let me kind of so maybe this is better explained by example. So these two conditions characterize truthful ordinal mechanisms, and what they say is the following. So supposing that everything else is fixed, player I changes its input from the first one to the second one. Okay? So we're going to say that the mechanism is not perverse if whenever a candidate goes up in the ranking, the probability of its selection does not decrease. Going up can only help the candidate. This is a natural thing. The other condition says that if something lower down in the ranking changes, the things above still continue to have the same probability. Right? So all my change is basically if something lower down changes, what the probability above does not change at all. So this is called. So the first condition is called non-perversity. The second condition is called utilization. Okay? And there was some really nice work done by Gibbard which said that truthful ordinal mechanism, they're truthful if and only if they satisfy both these conditions. So any mechanism which is localized and non-perverse is also truthful and ordinal. And there are actually stronger characterizations known as well for truthful ordinal mechanisms. The message over here is that truthful ordinal mechanisms we understand quite well. We have strong characterizations for these. These we understand. Cardinal mechanisms, the picture is quite incomplete. So for distortion, before our work, we didn't know of any works. I'm just going to talk about characterization for truthful cardinal mechanisms. So what's known as the following two results. Basically that if your mechanism is continuously differentiable, so the distribution changes continuously and is differentiable, then it's a distribution over unilateral mechanisms, which basically means that you pick a voter from some distribution, and then your output just has to depend upon the voter's utilities. Right? So that fourth thing which we said, if it's continuously differentiable, then any truthful mechanism has to be looking at that. It cannot do what the max mechanism was doing, which is that sum over all the utilities and do something based on. And some later work showed that this is also true if you want Pareto optimal mechanisms, Pareto optimal truthful cardinal mechanisms. So it has to depend upon, the mechanism has to pick a voter from some distribution and just look at that voter. But note that that these are necessary conditions; these are not sufficient conditions. So good characterization still is not needed for. Okay, so what do we do? So this is a couple of papers which appeared last year in roughly about last year. Yeah.
Even in the proof, it doesn't say anything about which single voter the mechanism should depend upon.
No, so it says it has to be a distribution over, and so mechanism 1 says I just look at voter K. Mechanism 2 says I just look at voter K. You can take a distribution, any distribution of this. So randomized dictator, for example. Okay, so what do we do? So remember that the lower bound on any ordinal mechanism with a truthful of naught was square root n. Right? So we show that you can get truthfulness without much additional cost. This gets square root log n. And this is true even in the case where you want to select more than one candidate. Like let's say you want to select the top k candidates. Again, you can do something similar. This is still in upper bound. I guess so what we also show is that this is tight. That earlier the square root n was shown for non-truthful. We show that in fact even this square root log n factor is required. So this is for ordinal truthful mechanism you cannot do better than square root n log n. And this depends crucially upon those two characterizations of truthful ordinal mechanism. Or you have the localization non-perversity. What I think is the more interesting result, which is that even for cardinal mechanisms which have all the information in the world, if you impose truthfulness, then immediately you get a loss of square root n. Okay, so the truthful cardinal mechanisms also have a distortion of omega of square root n. So if you impose either ordinal or truthful, you're going to suffer this much loss. And so note that this mechanism is also clearly a cardinal mechanism also. So this is an upper bound, right? So but the square root n and square root n again is an upper bound. I don't know where exactly the right number is between these two. I think that's an important question. But so one thing which we so we are trying to close this gap, look for square root n distortion mechanisms. And one thing which we wanted to address was that those characterizations which we have for truthful ordinal, this truthful ordinal have to be localized and non-perverse. Does that still hold for cardinal mechanisms as well? Does that still hold for do truthful cardinal mechanisms also have to satisfy those properties? Actually, it's non-trivial. And the answer we show is no. You can have really interesting cardinal mechanisms which get good welfare and everything, but which completely, which do not satisfy these properties. So basically, if you're looking for good mechanisms, you can't restrict your search space to mechanisms which just satisfy these properties. That was the basic message of this. This is terrible news. I mean, it's great if you're trying to get a paper out of it, but otherwise, square root 10 lower bounds are not great. Basically, it's showing that truthfulness involves a huge cost, right? Okay, so what if you next one we just said about this? So what if you kind of relax that? What if you look at equilibria instead? So equilibria is so this is the cardinal setting. Equilibria is known. So if you look at the worst equilibria, things can be pretty bad. What we show is, but there exists equilibria where the distortion is roughly about 1. So this would be more the price of price of stability, price of anarchy.
You look at like truthfulness and expectation.
For randomized mechanisms, it is truthful and expectation.
Okay, so let's see, so you get an output.
Yeah.
But still, like there's a distribution over.
For randomized mechanism, that's the case, right? So I'm comparing expected utilities.
So it doesn't like the extra level doesn't have any.
Unfortunately. I guess the small good news is that the mechanism which we all, which is natural, which we all like and understand, the max mechanism is what gives us this, this deterministic equilibrium which has distortion 1. Other results? Yeah, okay. Good. So I don't know. Yeah, we'll see how much time I have. This is in like descending order of how I would like to go through them. 1, 2, 3. But again, like the more important part is, I guess, the open questions at the end and filling questions you have. So I don't have to get too much. Okay, so let's look at what does the truthful ordinal mechanism look like? What is the non-trivial thing? And here's the mechanism. Like both the mechanism and the analysis fit on 2 slides. Here's what the mechanism looks like. The mechanism tosses a coin, tosses a fair coin. If it comes up heads, I'm just going to choose something uniformly at random. Ignore, throw away the input, pick something uniformly at random. If it comes up tails, I pick a voter at random. And instead of just looking at the top rank candidate, I'm going to pick a candidate with probability in inverse proportion to its rank. So I pick the first candidate with probability proportional to 1, second probability proportional to 1/2, 1/3, 1/4, and so on. So if you want to remove the proportionality, it's only 1 over log n, 1 over log n. That's it, that's the mechanism. So this is a truthful and has distortion of order square root n log n. The truthfulness is something that, again, like stare at it for 2 minutes, you should be able to convince yourself. I'm not going to spend the time on that. I will talk a little bit about why we get a distortion now.
Truthfulness is just based on the characterization.
Truthfulness is just based
It's
on the
not
characterization.
random.
Sure. Yeah. Right. So, I'm going to spend 2 minutes on the analysis of the distortion because the similar analysis goes through in the second part as well. There are a lot of commonalities. So why do we get distortion? This I'm going to look at 2 cases, and again, this is something which is repeated. If I have small, if my optimal welfare is small, then I do great because of my random choosing, because I get at least n over n. I'm not going to make a terrible choice. I make a reasonably okay choice. So, so then in this case I get n over n. This is a square root n log n approximation in this case. Right? Great. Now supposing that I'm in case 2, right? My optimal actually has large social welfare. Then what do? Okay, so let's say that this J star is my optimal candidate. Opt is the social welfare of J star. So here's something worth noting, that because of the unit sum assumption, because sum of utilities is 1, the utility of my jth rank candidate is at most 1 over its rank, which is well. The utility of candidate J is at most 1 over its rank. Because all of my previous ones, they rank above me, so they have at least as much utility. Right? So candidate 1 has utility at most 1, candidate 2 has utility at most 2, and we talk about rankings. Second rank candidate has utility at most half, third rank candidate has utility at most 1/3, and so on and so forth. Okay, so I'm actually going to just ignore all of the other candidates and try and just get a bound on this, on what is the probability that I actually select the optimal guy. What is the probability that I actually select J star? So from a mechanism, it's a probability that I pick a certain voter times the probability that I pick J star, given that I picked I, which is exactly this. 1 over n is what voter, and then this is sum over all voters of probability that I picked that. So if I remove the constant of proportionality, again, as I said, we get a log n over here. And by doing this substitution above, rank versus utility, I get that this is at least the social welfare of J star. And then this is actually all I need. So I plug this in over here. The solution is at most the optimal thing, which is social welfare of J star. The utility I get is at least the utility, expected utility I get from J star. So which is the welfare of J star times the probability that I pick J star. I plug in things over here and blah blah blah. I get my distortion. So I guess two things to know. One is that the framework of the proof says that again I have these two cases: small social welfare, large social welfare. Small social welfare, my uniform mechanism does fine. I'm happy with it. Large social welfare, I just look at the probability that I actually pick the optimal candidate, and somehow that's enough to be my
Why did you use the fact that social welfare is large in this kind?
Where did I use the fact that social welfare is large in this? That's a good question.
Last. Ah, okay.
Yeah.
So,
Okay. Right. Thank you. Okay. Good. Okay. So, right. I guess one other thing which is worth noting over here is that so this mechanism where you pick things in the probability inversely proportional to the rank. This is something that comes up in a lot of mechanisms, not just in social choice theory, but it's used. Yeah, I believe it's used in learning theory as well. It's used in similar kinds of things are used in prediction markets as well. So this kind of harmonic method of picking things turns out to be pretty useful. Especially when you want to gauge height. Sorry.
Can we do anything better? It's sort of rank coin, but a biased coin like with probability P return a random candidate and 1 minus P probability to the return.
You might get better constants. Yeah. But the lower bound says that you won't do better than square root n log n. Okay, so right, so let me move on right now. So this is part one, and this is the upper bound for ordinal truthful mechanisms.
the scaling is very crucial, right? It's if you just had that between 0 and for the
This particular. Yeah, so the unit sum gives us that the rank and utility are related. Otherwise, at least that happens. Okay, so let's look at cardinal truthful mechanism. Like I said, so the mechanism we saw is a cardinal truthful mechanism which gets square root m log n. I'm hoping that that this is a mechanism which does something. So that the earlier mechanism satisfied localization and non-perversity. I'm going to violate these two conditions. So let's see what that means.
Communication or the query points is extremely efficient. And you're only querying one candidate.
With one candidate, I'm asking for all of its references, but yeah, I'm picking this one candidate.
Yeah, but this is like super efficient in terms of query.
That's true. That's true. Yeah. Yeah, the amount of communication n is just thrown out of the window. It's just n log n.
It's impressive. The query is independent of M.
It's yeah, there's no dependent on it's true. Okay, so right, so let's look at this. So this mechanism does that fourth mechanism which we had seen earlier, that we fix a range for my distribution, and I'm going to pick from within this range. I'm going to pick the distribution which maximizes motorized expected utility. What is my range? So this is based on some earlier mechanisms which were studied by Barbara as well as Feige, suggested something like this, which is that, so this for three candidates, I know that my distribution is this two simplex. I'm going to look at the ball which is centered at one third, the maximum size ball, and this is my range. So I'm going to, for any utility that you give me, that still lies within, so like the simplex, again, because the unit sum assumption. I pick the point which maximizes this voter's utility, which is going to be this point, and that's what I done. Which is great. So these numbers show that this is non-localized and perverse. I don't think that the exact calculation is that interesting, so I'm going to skip one of these slides here. Just want to find what it said for us afterwards. Yeah, so okay, so sorry, I skipped a few slides in between, but let's get back to this. So this is great. The problem is that as my dimension m increases, the radius of the ball I can enclose within this simplex goes to zero, right? Which means that if I stick to this, then as I'm going to larger and larger, I'm basically just going to be picking uniform distribution again, which we know has terrible distortion. So I can't really do this. So I do the next obvious thing, which is that I allow my ball to kind of grow outside my simplex. But obviously, I just look at the parts. But I just look at the part of this ball which lies within my simplex. Right? So this is what I'm going to call a truncated hypersphere. Okay. And again, I do the same thing. Pick a modular uniformly at time and pick the point on this hypersphere which maximizes expected utility. What radius do I pick? Earlier it was the largest radius contained inside, so now I'm clearly not doing that. The problem is that I can't pick a particular radius. So we can show that if you fix a radius, then any hyperspherical mechanism, which is what we call these, has distortion m to the 3/5. Right? So anybody guess what we do next? Like I do what everybody does when we can't do anything, we can randomize to various things. So this is actually the randomization. Again, the same thing, toss of heads. So this is now the mechanism. Right? This is the randomized hyperspherical mechanism. I toss a coin. Heads, I just pick a random candidate. Tails, I'm going to take a radius from this set. It increases exponentially. So there are log n choices. Right? So I pick a radius, I pick a random motor I. From this truncated hypersphere defined by this radius, I pick the one which maximizes expected welfare. And this does what I hope it does, which is that it gives me distortion of order square.
Any intuition of why this works, even the Barbara's thing, why does it work?
So why it gives this distortion?
Why is it sort of useful to look at like the sphere contained in this?
I mean, let me show the proof. I think that it's a little intuitive why it does that. It's a one slide proof, so then you can come back to this. Again, truthful is easy and maximize I is expected. Two cases. First one, the social welfare is small. Again, uniform distribution is good. Skip this. Second case, social welfare is large. J star is the optimal candidate. And again, I'm just going to be looking at J star, trying to get a bound on how likely is it that I pick J star. So let's
potentially improve the distortion if you had a sense of how big the output was. In a sense, it's sort of the heads is always wasting.
It's wasting half, right? It's not. I mean, it just gives a factor of 2 extra.
But I'm wondering, maybe for cases where, say, I tell you that the filter is quite large, I mean, n over square root n is, yeah.
I don't see intuitively when you say that. I feel like so the welfare is quite large. Then I'd better be picking that thing which has large welfare. You know, I mean, it's not likely that the welfare is distributed among these candidates. There are maybe one or two or three or something. So I better be picking the candidate which has large welfare. Which means that that probability is the right thing to focus on.
It's like the reason why I asked was like in combinatorial option setting, they have this idea where they sample a few people just to get a estimate of. It's just, I mean, the analogy here would be you actually sample a few voters and tell them upfront, no, like anything you report, I won't.
What does that mean?
Yeah. So in this case, it's slightly complicated.
Yeah, yeah. Right. So for the analysis, like I said, I want to focus on the probability that this optimal thing is actually selected. And what I show is again that this is, you know, if you recall, this is similar to the probability that we have in the ordinal case as well. I'm going to show that this holds over here as well. Once I have this thing, the same set of inequalities goes through. So let me so basically what I want to show is exactly this probability. I'm going to hand wave a little bit, but the statements I make are not exactly true, but they can be roughly true. Which is that um, so so when you look at what is I's utility, there's some UI and there's some UI by 2. UI by 2 will not lie exactly between on this line, midway between this line, maybe UI is 0, but let's use it as 0. So then I know, because I'm doubling my radius every time, right? Because this set consists of 0, 1 over m, 2 over m, 4 over m. Between UI and UI by 2, there's going to be some hypersphere that I take. I pick the property 1 over log. If I do that, if I pick this particular hypersphere for motor I, then the probabilities are going to lie between UI and UI by 2. The probability that I pick J is going to be somewhere between Uij and Uijy. So this exactly equals. So therefore, I get the probability that J is selected is, like I said, and this is, you know, the probability that this particular hypersphere is selected. Okay. Again, I plug this in, I sum this over overall voters, and this gives me what I want. So this gives me the probability of actually selecting voter I is going to be Uij, the social welfare of G. Which is what I need. I plug this back in. This works.
Why a sphere, like you couldn't pick other just like book you?
The spheres were easier to work with. It's not other shapes we found were less easy to work with. And it's not obvious that that a polytope would satisfy this property, right? That it will have between.
Not polytope would take the hypercube, like the center.
I'm not completely certain. I'm not completely certain that it will satisfy this property. Anyway, okay. So this works. Right. So this gives us a square root n bound. It's truthful and satisfies all of these things properties. So we had high hopes of this kind of mechanisms. We thought it would do something else as well, but we weren't able. But I talk a little bit at the end of what those other hopes were. Okay, so I talk a little bit about this distortion. I won't get into the proofs of this. I think that two proofs is maybe one too many for a talk. But so here's the max mechanism. You ask everybody for the utilities, pick the candidate which has highest utility. If there's a tie, then you have some ordering on the candidate, you pick whichever one is higher than And I said, yeah, so like I said, if I just look at equilibria for these, then equilibria can be pretty bad. Again, just to think about it, say that every single voter agrees on a terrible candidate. Everybody says that this is my best choice. It's terrible, but one person cannot change the outcome, so that's making it. Okay, so here's so the equilibrium which we look at, which we say has nice, which has good distortion, is the one we get with the following dynamics, which is that supposing that voter I wants to deal with, voter I doesn't like the current candidate, by changing its vote, it can make somebody else win. If it can make J win, then clearly one way it can make J win is by transferring all of its utility, which is 1 to candidate J. So I focus on dynamics where that is what every voter does. If it changes its vote, it shifts to a plurality. It shifts to a plurality vote where all of its utility is on one single candidate. And this, right? So each voter deviates to binary vote, and this we show two things. Firstly, it converges to a Fibonacci equilibria which has this distortion, so it's nearly 1. Opt over opt minus log n. Note that opt again is at least n over m. Right? So for n large enough, this is very close to 1. And secondly, the fact is that this does so it converges in something like n cube steps. Right? So it doesn't take a long time, and it converges to something nice as well. Right? So maybe yeah, this max mechanism is not. And like we at least thought that this kind of deviation also makes a lot of sense. Like if I'm going to deviate, I'm not going to compute some, I mean, like one obvious way to deviate is this, that I just put all my vote on the candidate I would like to win. So I thought that was a natural dynamic. Okay, so like I said, I'm going to skip the proof of this now. But this was our result for at least equilibria. So truthfulness, not good from the point of view of social welfare. Equilibria may be something better. Okay, so nearing the end, this is a recap of what we talked about. There are some other results as well. It has results about
Nash equilibrium is like honest Nash in the sense that there every deviation is possible.
Yeah. Because if a deviation is possible, then a binary deviation is possible.
But all I'm saying is that the dynamics there's a strong result in the sense that you don't have to look at complicated dynamics, but the equilibrium that you get to is like a genuine equilibrium.
It is a genuine. It is a Fibonacci equilibrium for whatever definition of deviation you think. Right. Okay. So let me ask some open questions over here. So firstly, like I said, so for cardinal mechanisms, I mean, it's just a square root log n bound. I think that to close this square root log n bound, you will need to provide some interesting characterization of cardinal mechanisms. So I think this is an interesting open question. If you can close this, I would be very interested in that. And I think that this would lead to or would require better characterizations of truthful cardinal mechanisms. We spoke a little bit about Nash equilibria. I'm interested if you can relax the particular dynamics. What relaxations of those dynamics can you still get polytime convergence as well as good equilibrium? Or even approximate truthfulness, like some small multiplicative deviations are discouraged. The other thing, the other set of questions which again I think are interesting is that, so we talked about the unit sum assumption. Another common assumption is unit range. Unit range basically says that all your utilities may not sum up to 1, they just lie between 0 and 1. Right? And in particular, that your lowest utility is 0 and your highest utility is 1. So this is, I find this interesting because on the one hand, you think that because it's not restricted between 0 and 1, it gives you more flexibility, so the distortion should be larger and so on and so forth. The problem is that it also fixes, sorry, this should be 1. This is what happens when you do slides a minute before. Sorry, so the max should be 1. But because you fix the minimum and the maximum utility, at least in the two candidate case, ordinal equals cardinal. If I tell you what my ordering is, you know what my utilities are. Right? Even in the three candidate case, I just have to give you the utility for the middle one. I don't have to tell you anything about the others. Right? So somehow this has both less information and more information than our unit sum case. This is perhaps reflected in what we know about these. For example, again, sorry, for truthful cardinal mechanisms, the best upper bound known is m to the 3/4. The lower bound is something like log n. It's actually log n by log n. So can you do anything better than this last gap? In general, like all of the things we've looked at, there is less work for the case of unit range vectors. So yeah, so those results I think would be interesting as well. But yeah, this is, let me just stop here.
I have time for a few questions. So the square root m, the ordinal one also in some sense uses this assumption. No?
The UIJ versus the rank, yeah, absolutely.
So even
I don't know what the correct answer is.
and this lower bound, like m to the 3/4 that you just mentioned, it's again for cardinal.
Yeah.
So it can even be worse. So the unit range assumption ordinal.
Yes.
It can be worse.
I don't know where. I mean, these bounds are develop worse, better. I don't know where the right answer is. Yeah, sorry. So which I want to mention. So when he came up with the hyperspherical mechanism, there's a way. I mean, like one way you can think of is that you have unit range, but that's fine. You can just normalize them. Right? You can divide them by the sum, and you can get back to unit sum. So we tried running the same mechanism hyperspherical on the scale unit range voters, but yeah, we weren't able to completely analyze it. So that I would be interested in what that is.
Are other welfare functions interesting beyond social?
Yeah, of course. I mean, yeah. So for example, I mentioned that you select K candidates. Right? So what we worked with was the case where you select K and you sum the social welfare over these K. But you could say that if you look at these K, my utility for these is the mean amongst this K. Right? So yeah, so that I agree. That I agree would be very interesting as well. I don't know what the right answer is.
Distortion would be then defined according to
Similarly, worst case overall utilities.
I just want to understand the definition. Like, so for ordinal, truthful ordinal mechanism, the bounds of distortion root and log n.
Yeah.
Like as soon as you go to ordinal, you get root n loss, and then for truthfulness, you get additional root log n. But in cardinal truthful, like for cardinal, obviously you don't have any distortion, but for truthful, you just jump to root n directly.
Yeah.
I mean,
basically that truthfulness is costly. Whether
no, because going from ordinal to truthful, there was just root n.
because you already lost. Yeah. So I don't know. I mean, you already lost what you had to. So truthfulness is like, okay, fine. I don't want to make this up. But yeah, I mean, I'm joking. But yeah, it would be good to have a more formal explanation.
If there are no more questions, let's thank Umang again and as a token of appreciation from IISc.